Okay, 11.3, the last topic that I have to cover is estimating the sum of the series. It is not always possible to find the exact sum of a convergent series. We can, however, estimate the sum of a convergent series by a partial sum of the series. So by adding enough many terms of the series, we can estimate the exact sum of the series if we know that the series is convergent. So then, let's say I have a series an, series n going from 1 to infinity of an, and let's say this is a convergent series, and let's denote by s the sum of the series. Now, what's the meaning of s, by the way? The meaning of s is that s is the limit of the nth partial sum as n goes to infinity, right? That's the meaning of s. So that's the sum of the series, and we are going to estimate the sum s by the nth partial sum. So Sn is a1 plus a2 dot 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 an, sum of the first n terms, and we are using that as an approximation to the sum of the entire series, right? So if I do that, if I estimate s by using Sn, then I need to know how good my approximation is. Okay. So in order to understand that, let's do the following. Let's denote by Rn the error when you are doing this estimation. So what is Rn then? Well, Rn is the difference between s and Sn then, because you are using Sn as an estimation of s. So the difference between s and Sn will be the error. So let's say Rn is that. So what is Rn then? Rn is the error, and then Rn will be s minus Sn. Now remember what s is. What is s? S is the entire series, right? S is the entire series. A1, A2, A3, dot, dot, dot. And what is Sn? Sn is the sum a1 plus a2 up to an. So when you take the difference, what do you get? You get the remaining term. So Sn is the first n terms, and S is the entire series. So if you subtract the first n terms from the series, right, you get the remaining terms starting from the n plus first term, right? Is everybody okay? From the entire series, you are subtracting the first n terms. You are left with the remaining terms starting with the n plus first term. So Rn, the error Rn would be given by summation k going from n plus 1 up to infinity of ak. And let's see what's the limit of Rn as n goes to infinity. Well, the limit of Rn as n goes to infinity is what? The limit as n goes to infinity of s minus Sn, because that's how we defined Rn, right? Rn is the difference between s and Sn. And what's the limit of s? Well, s is a constant there, so the limit of s is s. What's the limit of Sn? By definition, the limit of Sn is s. So the limit of Rn would be 0. The limit of Rn would be 0. So what is it telling me? Well, it's telling me that the error Rn is approaching 0 as n goes to infinity. Okay? Which means it's not a bad idea to approximate the sum of the series S by using the nth partial sum, because the error is going to 0 as n goes to infinity. Which means by picking n big enough, we can get a good approximation of the sum of the series. However, that's not good enough. I need to know if I can quantify the error. How big my error will be if I use only the first 20 terms. How big my error is. So I have to do that. So in order to do that, that's not possible always, but in some cases it is. So let's see when we can come up with a bound for the error. So in order to find out how good the approximation Sn is for S, we need to be able to find bounds for the error Rn. Rn is also called the remainder. And we could do this when we can apply the integral test. So let's say I have a function f which is continuous, positive, and decreasing on the interval from 1 to infinity. Let's say I am defining a sequence an by taking an to be the same as f of n for n bigger than 1. Assume that the improper integral of f from 1 to infinity is convergent. Then by the integral test we know that the series n going from 1 to infinity of an, this series, notice that is the same as the series n going from 1 to infinity of f of n. So this series is convergent by the integral test. Okay, so because it's convergent, we can think about approximating the sum of the series. Let's say S is the sum of the series, and let's take Rn to be the error S minus Sn, which would be then what? Rn would be an plus 1, an plus 2, plus an plus 3, and so on. So that's the remainder or the error when you use Sn to approximate S. Is everybody clear? Now, what's the meaning? What's the graphical meaning when we say that the improper integral of f from 1 to infinity is convergent or finite? Well, because the integral of f from 1 to infinity is finite, it means that the area below the graph of f from 1 to infinity is what? Finite, right? Because the improper integral of f is finite, we are assuming that, so the area below the graph of f from 1 to infinity is finite. Okay, now I want to come up with an approximation for Rn, right? So let's see how we could do that. Let's look at the left-hand side figure. I have the graph of f. Remember, f is positive, decreasing, continuous. So the graph of f will look like that. Now, look at the graph of f from n up to infinity, from n to infinity, and divide the interval from n to infinity into subintervals of length 1. So you go from n to n plus 1, to n plus 2, to n plus 3, and so on. Or above each subinterval, draw a rectangle where the height of the rectangle would be the same as the height of the graph of f at the right-hand point. So if you think about it, then what's the area of the first rectangle? If you look at the interval between n and n plus 1, I am taking the height of the rectangle to be the height of the graph at n plus 1, which would be this. So what is that? That is f of n plus 1, right? The height of the first rectangle is f of n plus 1. But remember, f of n plus 1 is the same as an plus 1, right? We defined an plus 1. We defined an by taking an to be f of n. So then I know that the area of the first rectangle would be an plus 1. What would be the area of the second rectangle? An plus 2. The third rectangle, an plus 3, and so on. So what's the total area of the rectangles? It will be an plus 1, an plus 2, an plus 3, which is clearly less than the area below the graph of f from n to infinity. The total area of the rectangles would be less than the area below the graph of f from n to infinity, which is given by the integral from n to infinity of f, right? But I know that that integral is finite, n to infinity, because the integral from 1 to infinity of f is finite, is assumed. Well, if that's the case, then what can I say about the remainder term? Well, this is exactly the remainder term, right? Rn. So Rn is then less than the integral from n to infinity of f dx. Okay, so that I obtained an upper bound for Rn. Let's obtain a lower bound for Rn. So now my goal is to get a lower bound for Rn. How? Instead of starting at n, I am going to start at n plus 1, Okay, and I'm going to look at the interval from n plus 1 to infinity, divide the interval into subintervals of length 1 again. So I get n plus 1, n plus 2, n plus 3, and so on. On each subinterval, draw a rectangle where the height of the rectangle is the same as the height of the graph of f at the left-hand point. So here, what's the height of the graph? The height of the graph for the first rectangle here is f of n plus 1, right? Which is the same as an plus 1. And that's the area. So the first rectangle has area an plus 1. The second one has rectangle area an plus 2. And so on. Which is greater than the area below the graph of f from n plus 1 to infinity. So I have this inequality then, that Rn is greater than the integral from n plus 1 to infinity of f of x dx. So I got a lower bound for Rn, I got an upper bound for Rn. Is that clear? What's the difference between the two integrals? Which integral is bigger? Remember, f is positive. This one is bigger because the interval of integration is bigger, right? This interval, n to infinity, is bigger than the interval from n plus 1 to infinity, right? Between n and n plus 1, you have a gap of 1, right? So the interval, the integral for the upper bound integral is bigger than the lower bound integral, for sure. So what did we get then? We got that the remainder Rn, which is the same as s minus Sn, is in between two integrals. One is integral from n plus 1 to infinity of f of x dx, and it is less than the integral from n to infinity of f dx. And from this, so that means s minus Sn is in between the two integrals. I can add Sn on both sides, and I can come up with a bound for s. So now I know that s is between Sn plus integral from n to infinity of f and Sn plus integral from n plus 1 to infinity of f. So remember, what is s? S is the actual sum of the series, and we got a bound for that. Now all this can be done only when what? Only when what? All this could be done only when remember what we assumed, only when my sequence an is given by f of n, f is positive decreasing continuous, right? And the integral of f from 1 to infinity is finite. Only then I can come up with those bounds for Rn. Otherwise I can't. Is everybody clear? So what's the summary of all that? The remainder estimate for the integral test. Again, suppose that ak, the sequence ak is given by f of k, where f is a positive decreasing and continuous function for x bigger than or equal to some fixed number. There's a bad notation here, and I don't want to use the same n here. Let's make it big N. So all we are saying is that the function f is a continuous positive and decreasing after some point on. Okay? And then the series, let's assume that the integral of f from 1 to from the improper integral of f, let's say, is finite, then the series would be convergent. The series n going from 1 to infinity of an would be convergent. And then if Rn is the error when you estimate the sum of the series S by Sn, then Rn satisfies those bounds. Oh, I see. Okay, no. This n is fine. Sorry. This n is fine. Because remember our picture, as long as the function f is decreasing after n, I can do all that calculations that I did. Okay, so yeah.
So I'm kind of lost. What's the difference between f of k and f of x and f of n, or a of k or a of n?
Well, a of k and a of n doesn't have really any difference, because a and ak, it's just I'm using different symbols for the index. But when we are saying f of k is ak, all I'm saying, my sequence, the terms of my series are given by f of k. So f of k means k represents a positive integer there. So k could be 1, 2, 3, and so on. Whereas f, the function f, is defined for the entire interval of real numbers from 1 to infinity. So when you write f of x, you're thinking of x taking on any value from 1 to infinity. When you're thinking of f of k, you're only thinking of k as a positive integer. Right? Well, the values are the same. So f of k is the value of the function f at k, right? But I'm saying that when you're writing k, you're thinking of k as a positive. So you're looking at the value of the function at positive integers versus the value of the function at any real number. Am I making sense? So you're asking me what's the difference between f of x and f of k, right? Right? F of x is a function. Let's say f of x is 1 over x squared, right? So x could be 0.1, 0.2, it could be 1.3, 1.5, right? However, if I am writing f of k, I mean k is an integer. So for example, we are saying f of 2 is 1 over 2 squared, right? So that is, I am looking at the values of the function f at only the positive integers to come up with the series, right? The terms of the series are given by the values of the function at the positive integers. That's what we're saying. Let me give you an example to maybe that's going to clear it up. So let's look at an example of this. Let's say I have a series here. Summation n going from 1 to infinity of 1 over n cubed. So the series I have here is the series summation n going from 1 to infinity of 1 over n cubed. Okay? Is everybody okay? Now, if I take the function f of x to be the function 1 over x cubed, where I am taking x to be any real number bigger than 1. Okay? Notice then the terms of the series are basically the values of the function f at the positive integers, right? So what is the nth term of the series? The nth term of the series is the same as f of n. The nth term of the series is the same as the f of n. Okay? Is everybody okay with that? Now if I look at the improper integral of f of x, which is 1 over x cubed, from 1 to infinity, then I know that it's convergent. You can do the calculation, you'll see that this integral is convergent. You can also use this series is convergent. And because this series is convergent, then we know that the series given by the sum of 1 over n cubed is also convergent by the integral test. Or you can say that this series is convergent by the p-series test. Okay? This is the p series with p equals to 3. So we saw that p series will converge when p is bigger than 1. Is everybody okay? So I have the function f of x here, which is 1 over x cubed. The relationship of the function f with the series is that every term of the series is a special value of the function. Each term is the value of the function at some integer. Is that making sense? So now that we know that this series is convergent, we don't know the exact sum of the series, but we want to estimate the sum of the series. So let's estimate the sum of this series by using only the first 10 terms. So I am estimating this series by using S10. So if I do that, what do I get? I get 1. What is the first term of the series? 1. The second term of the series is 1 over 2 cubed. The third term of the series is 1 over 3 cubed, right? And so on all the way up to 1 over 10 cubed. That's S10, the sum of the first 10 terms, the 10th partial sum. If you do the calculation here, you're going to get 1.1975. Okay? I recommend using a calculator for that, or a computer algebra system. Okay? So now I want to know, I am estimating the actual sum. Whatever the actual sum, I don't know. I'm estimating that by using S10. What's the error? Well, the error, I'm going to denote that by R10. The R10, the error would be S minus S10. S is the actual sum. S10 is the 10th partial sum. So if I subtract the 10th partial sum from the entire series, right, what do I get? I get all the terms after the 11th term, right? I am left with all the terms after the 11th term. That's R10, that's the error. Well, how big is that error? Well, we know that R10 has to be what? R10, let me go back to the formula here. We know that Rn has to be less than the integral from n to infinity of f. Integral from n to infinity of f. So, I could say that R10 is less than the integral from 10 to infinity of 1 over x cubed dx. However, the integral from 10 to infinity of 1 over x cubed dx is very easy to compute. What's the antiderivative of 1 over x cubed? Negative 1 over x squared. And if you compute the integral, you'll see that you get 1 over 200. So this integral is 1 over 200, which is 0.005. So then I know that the error R10 is less than 0.005. So what is the meaning of all that we did? Well, basically, whatever the actual sum of this series is, if we are using S10 to estimate that, which is 1.1975, if we are using this number as an estimate, then the maximum error is less than 0.005. Then the error is less than 0.005. Is everybody okay? Is everybody okay? Now, you have to be careful here when you're using R10 less than this integral. The only reason we could do this is because the terms of my series is given by a function f, and that function is positive decreasing continuous, and the improper integral of that function is what? Finite. Otherwise, you cannot use this. Okay, your terms must be given by the values of a continuous decreasing positive function, and the improper integral of that function must be finite. Otherwise, you cannot do this. Now, part B of this same question is that we saw that if I use only 10 terms, then I get an estimate of the actual sum of the series, where the error is as bad as 0.05. Right? It's no worse than 0.05, the error. And the second part of the question is, how many terms do I need to add in order to ensure that the error would be less than 0.0005? So one more zero. So when I added 10 terms, my estimate, the error I got was 0.005. So how many terms should I add to make sure the error is less than 0.005? Okay? 0.005. How do I come up with that? Well, so then what am I doing? I'm using the nth partial sum to estimate the actual sum of the series. So the remainder or the error would be S minus Sn. The question then is, how large n needs to be to get Rn to be less than 0.0005? We know from our formula is that Rn is less than the integral from n to infinity of 1 over x cubed dx. And if you compute the improper integral, you are going to get 1 over 2n squared. Okay? So then what do I have? I have Rn, the error, is less than 1 over 2n squared. And as long, so the question then I ask is how big n I need to make sure that 1 over 2n squared is less than 0.0005. So that means I want to know how big n needs to be so that 1 over 2n squared is less than 0.0005. And I can solve for n. I see that 2n squared would have to be bigger than 1 over 0.0005. 1 over 0.0005, and then n squared would be greater than 1 over 2 times 0.0005. Then n squared would be bigger than 1 over 0.0001, which is the same as 1,000. And if n squared is bigger than 1,000, then n has to be bigger than root of 1,000. And then n has to be bigger than 31.6. So how many terms do I need to add in order to ensure that the error is less than 0.005? Sorry, 0005 would be how many terms? 31 or 32? 32. In fact, you have to pick the bigger one because you need n to be at least as big as this to ensure so you have to pick n to be at least 32 to ensure the desired error. Okay? Any questions now? 1 over 2n squared. Let's see. Where? Right here. This 1 over 2n squared. So you're looking at this integral, right? So integral from n to infinity of 1 over x cubed dx, right? Which is the same as the limit as t goes to infinity n to t 1 over x cubed dx, right? And notice that what is this integral then? The antiderivative of that integral would be negative 1 over x squared, right? No, it is what? X to the negative 3, so negative 3 plus 1 over negative 3 plus 1, which is, I get a negative 2 as well. So this would be plus, this would be a 2x squared here. This would be a plus. No, this would be a negative, sorry. This would be a negative. Negative 1. So now I have between t and n, right? So now you plug in n and t, right? If you plug in n and t, what did you get? And subtract. What you're going to get is you're going to get negative negative 1 over 2t squared, and then plus 1 over 2n squared, right? And then when you take the limit as t goes to infinity, you are left with 1 over 2n squared. Is it? Yeah. Yes. Take the antiderivative first, and then evaluate the antiderivative at the upper limit, lower limit, and then subtract. And then at the end, you're going to take the limit as t goes to infinity. Is everybody okay? All right. So, any other questions at all? Is everybody done writing it down? Did everyone get the handout that I gave today? Everyone has a copy of that? Okay. Any other questions on this? In your homework from this section, first of all, at the web assignment, there is a video example, another video example on this. So you should watch that again. And then there is another problem where you have to do it yourself. Okay? All right, so that's the end of 11.3.